All right, we're continuing with the sections 13.5 and 13.6, and we're just still working on exercises. So we are working on 13.6. We're going to do number 28. So we're on page 868. 28, which says, in exercises 27 through 30, find a vector that is normal to the graph of f at the given point, and they give us f of x, y equals 4 minus x squared minus y squared. The square root of all of that. And this is at the point -1, 1, square root of 2. So -1, 1, square root of 2 is our point that we're given. So notice the difference between this problem number 28 and then problems 24 through 26. And all of those, they have their function is set equal to some constant. So we'll have something like this equals a constant. And in that scenario, you would just, your normal vector that you're looking for is just the two-dimensional gradient vector f sub x comma f sub y. Now in this scenario, we are looking at z equals some function of x and y. So when we look at our gradient vector, we're going to move everything to one side and we'll have a three-dimensional gradient vector. So this is z equals 4 minus x squared minus y squared to the 1/2. And you move everything to the left or the right. It doesn't really matter. The convention, though, is to move everything so that your z has a negative sign in front of it. So for us, that would be moving everything to the right, although I'm going to write it on the left. So that's 4 minus x squared minus y squared to the 1/2 minus z equals 0. All right, so now what we're going to do is we want to find our gradient vector of this. So the vector that we're going to be considering our normal vector that we want. So n, we're going to call it this, but we're just going to call it capital N, for us is going to be equal to, now I don't want to use f sub, I am going to actually use that. I really want the partial of this with respect to x, but notice if I take the partial with respect to x, this is going to be 0. So it's really just going to boil down to being the partial of this with respect to x, which is the partial of that with respect to x. So it truly is f sub x. Then the partial of this with respect to y is going to be 0. So it really is just f sub y. And then the partial of this with respect to z is just -1. So that's what that vector is going to be. And you'll see this vector quite often. So now we actually need to go ahead and take our partials. And then we're going to put our point in there. So this equals partial of this with respect to x, or this with respect to x, whichever way you want to look at it. So that's going to give us 1/2 times the derivative stays the inside, raised to the -1/2, and then times the -2x. So this is going to simplify, but I'll just write it all out first. I'm going to simplify the next one. 4 minus x squared minus y squared to the -1/2, and then times -2x. Partial with respect to y is going to be nearly identical to this, with the exception of this x is going to be a y. But to see what that's going to look like, let's just cancel those. So in this, we're going to get the same thing, but now it's going to be -y over the square root of 4 minus x squared minus y squared. So -y over the square root of 4 minus x squared minus y squared. This simplifies to be the same thing with the exception it has an x in the numerator. And then that's just -1. So there's nothing to do there. Now we take our point that we have and we substitute the x and the y in here. Now bear in mind, this point, -1, 1, square root of 2, don't be alarmed by the fact that that and that don't match, because this point corresponds to this function right here. Now you should be alarmed if you plug -1 and 1 in here and you don't get square root of 2. That's what this is. So this is x, y, and the corresponding z, you put those in there. This will not correspond to that. This is some normal vector. That's just a point on whatever this graph is. All right, so our normal vector, we're going to plug the x and the y in here. There's nowhere for us to plug that in. It's just telling us if we were to sketch this thing right here, and then we sketch that, and then we're at the point -1, 1, square root 2, then a normal vector at that point is going to be this vector that we get down here. So this would be the vector that we would use to find the tangent plane at that particular point on this surface. So what do we get here? Let's see. We are putting in x is -1, y is 1. So we're going to get 4 so we're going to square root of 2 in the denominator, and we're putting in 1 for our x. So we're going to get 1, or -1, excuse me, -1 for our x. So we are going to get 1 over the square root of 2, because we have a negative sign right there as well. And then comma, we're putting in 1 for our y. So -1 over square root of 2, comma, -1. So that will be the normal vector if we want to find the tangent plane to this surface at that particular point. All right, so next, let's look at same page, number 34. So number 34 says, in exercises 31 through 38, find the equation of the plane tangents the graph of the given function at the indicated point or points. All right, so now we are going to find a normal vector, and we're actually going to take it a step further and find the equation of the tangent plane. So for 34, they give us f of xy equals e to the x plus y squared, e to the x plus y squared. And they give us 2 points. They give us -1, 0, e to the -1, -1, 0, e to the -1. We'll call that P1. And they give us another point, P2, which is 0, 1, e. 0, 1, e. All right, so first, let's just find our normal vector. And notice this is similar to the previous problem where we have z equals some function of x and y. So now we would just move everything over to where our z was negative, and I'll write it out the same way we did the last one. So z equals e to the x plus y squared. You don't have to rewrite it this way if you don't want to, but I'm just trying to make it clear as to why our normal vector turns out to always have that -1 for its k component. So this is e to the x plus y squared minus z equals 0. So our normal vector is f sub x, comma f sub y, comma -1. And for us, the partial of this with respect to x, meaning we just really need to look at that thing, is we take the derivative of this exponent with respect to x, and then multiply by this thing stays the same. So the derivative of that exponent with respect to x is just 1, and then times e to the x plus y squared. So we get e to the x plus y squared there. And then the derivative of this with respect to y, look at that exponent, take its derivative with respect to y, that's just going to be 2y, and then times this thing stays the same, 2y e to the x plus y squared. And then our k component is always going to be -1. All All right, so now what we need to do is we want to find the tangent plane to this thing at this point and at that point. So we're going to have to do two separate, we're finding two separate tangent planes, well, unless they happen to give you the same tangent plane, but we'll see that in just a second, which I don't think they could. But all right, so our normal vector, we'll call it n sub 1 for that particular point. So n sub 1 equals, what are we putting in? We're putting in -1 for our x and 0 for our y. So we get e to the -1, or 1 over e. Then we are putting in 0 for our y, so that whole thing turns to 0, and then -1. And we have our normal vector and our point, so now we can find the equation of a plane. So the equation of the plane will be 1 over e times x minus -1, so x plus 1, and then plus 0 times y minus y naught, so we don't need to write that, and then plus plus -1 times z minus z naught, so that's -1, and then our z minus our z naught is this point right here, so e to the -1, or 1 over e, and that equals 0. And you could simplify that if you wanted to, but that's perfectly fine to leave that like that. And now let's find the equation for the other plane. So we need n sub 2 equals, so now we're taking this point and we're putting it in here to find our normal vector. So when we put in x equals 0, y equals 1, we just get e. And then we put in x equals 0, y equals 1, so we're going to get 2e. And then we just have -1 right there. So now the equation of the plane, we're going to use this vector coupled with that point, and we have e times x minus x naught, which is x minus 0, so we're just going to have e times x, and then plus 2e times y minus 1, and then -1 times z minus e equals 0. And that's the equation of the tangent plane to this at that particular point. All right, so we'll stop this video here, and then in the next video, I'll continue doing some more example problems from sections 13.5 and 13.6.